In this video, we're going to cover section 11.5 on the preparation and reactions of acid chlorides. Now, acid chlorides can be formed by treating carboxylic acids with thionyl chloride, SOCl2. And you may recall that we used SOCl2 previously to convert alcohols to the corresponding alkyl chloride. This reaction has a lot of synthetic utility because there's not many ways in which we can convert carboxylic acids or any other functionality for that matter to the acid chloride. So this reaction is quite useful in the sense that acid chlorides are the most reactive species of the four carboxylic acid derivatives that we're going to look at in more detail. So this is a synthetically useful reaction because it allows us to prepare pretty much any other carboxylic acid derivative. Now let's look at some of the reactions of acid chlorides and just see how useful this particular species is for the formation of other functional groups. Now when we treat acid chlorides with water, they will be hydrolyzed to give us back the carboxylic acid. And so this hydrolysis reaction will convert an acid chloride to its corresponding carboxylic acid. Note that we also will include pyridine, a weak base, as a part of this process. And we'll see on the following slide the role that pyridine plays in this hydrolysis reaction. Now the mechanism for this transformation is basically our nucleophilic acyl substitution reaction, but the last step that we must include is a proton transfer step. So if we start with our water molecule, reacting in a nucleophilic manner, attacking the carbonyl carbon, breaking the pi bond to form our tetrahedral intermediate. Then we see reformation of the carbonyl and loss of the leaving group. And again, the leaving group will be the chlorine atom as a chloride, as shown here. Now what we're left with after that particular nucleophilic acyl substitution reaction is we're left with a species, basically the protonated version of the carboxylic acid. And so the additional step that we must include in this mechanism is a final proton transfer step in which water will pick up that proton, giving you the carboxylic acid. Now what's not being shown is the side product. We will also, in that proton transfer, form the hydronium. And this is where pyridine plays a role. So recall that pyridine has this structure. Pyridine being a weak base, it's going to remove the acidic proton from the hydronium to give you a water molecule and the pyridinium. Now this is useful because this will form a salt with this chloride. And so typically in this reaction, you'll form pyridinium chloride, which is a stable salt. And so this ensures that there's no acidity left over other than the final product, your carboxylic acid. And so we refer to this as a neutralization, where we're ensuring that there's no acidic protons left in solution. Now, instead of hydrolysis, if we were to replace water with an alcohol, this is a convenient way of producing an ester. And the mechanism is exactly the same as what we just saw for the hydrolysis of an acid chloride. We also will add alcohol in the presence of pyridine. And again, pyridine will be used as a weak base to neutralize any acidity in the solution. Specifically, it will react with the protonated alcohol in this particular case to form a pyridinium salt with the leaving group, the chloride ion. Now, when we treat an acid chloride with ammonia, we can convert an acid chloride to the respective amide. And again, the mechanism is exactly the same as what we just saw. Nucleophilic acyl substitution followed by a proton transfer. Now, in this particular case, pyridine is not required because ammonia, as long as we use 2 moles of ammonia for every 1 mole of acid chloride, is sufficiently strong as a base to neutralize any acidic byproducts. So long as we have that 2-to-1 ratio, 1 for nucleophilic attack and 1 to neutralize acidic byproducts, we can carry out this reaction in the absence of any additional species, i.e. pyridine. Now, this reaction also works with primary or secondary amines to produce N-substituted amides. So depending on what substitution pattern you want on the nitrogen of the amide, you would choose the appropriate amine to carry out this particular reaction. Now, similar to what we saw for ammonia, you would use it in a 2-to-1 ratio, meaning we would have 2 equivalents or 2 moles of the particular amine to 1 mole of the acid chloride. Now, similar to what we saw previously for carboxylic acids and esters, we can reduce acid chlorides with lithium aluminum hydride, and this will give us alcohols. So as shown, if we use excess lithium aluminum hydride and we follow that reaction with the addition of water, we can prepare a primary alcohol. And you may recall that the mechanism, as shown, was one of really a nucleophilic acyl substitution to start off, followed by a nucleophilic addition. So again, the aluminum hydride is being used as a hydride transfer reagent, and the electrons of this aluminum hydrogen bond, the hydride, will attack the carbon of the carbonyl, breaking the pi bond. That forms our tetrahedral intermediate, and then we see reformation of the pi bond and loss of our leaving group. And so these first 2 steps, we didn't introduce them previously as a new mechanism, but in fact, this is the nucleophilic acyl substitution. So the result of that first nucleophilic acyl substitution is the formation of an aldehyde. Now, with excess lithium aluminum hydride present, we have a second equivalent of that hydride attacking the carbonyl carbon, eventually the formation of our tetrahedral intermediate. And it's at this point that we can't have any loss of the leaving group because the hydride is a very poor leaving group. And so in the presence of water, or H3O plus, as shown here, we will have a quench of this particular intermediate species to give us the alcohol. You will see from time to time that either water will be used or the hydronium, a dilute acid, will be used in that second step. I'm not too concerned as to what the choice is. Generally, from an oxide, water is sufficient, but there is, on occasion, a preference for a dilute acid. I wouldn't worry about that particular step, so long as there's a proton source, whether it be a polar protic solvent or a weak acid, either is fine for me in that quenching step. Now, the reaction between an acid chloride and lithium aluminum hydride cannot produce the aldehyde. Even if we were to be careful and to use 1 equivalent of LAH, we will not end up with conversion to just the aldehyde. We'll end up with a mixture of primary alcohol and maybe a little bit of aldehyde. So to more cleanly prepare an aldehyde from an acid chloride, we must use a more selective hydride reducing agent. And the most common version of LAH that we use is this. It's lithium tri-T-butoxy aluminum hydride. And you can see that the main difference between LAH and this reagent is the replacement of all the remaining hydrogens with these T-butoxy groups. So this steric bulk reduces the reactivity of this aluminum hydride reagent. And so we have, again, one source of the hydride that can be used to carry out the reaction, but we don't see any successive reactivity with the aldehyde when this reagent is used. So it allows us to stop the reaction at the aldehyde stage and not proceed to the alcohol. So similar to the hydrogen nucleophiles that we just discussed, acid chlorides will also react with carbon nucleophiles, like the Grignard reagent and like organolithiums. And similar to what we saw previously, is that we can form alcohols if excess Grignard or organolithium is used to carry out this transformation. And so similar to what we saw previously, we have the carbon nucleophile attacking the carbonyl carbon of the acid chloride, breaking the pi bond, forming our tetrahedral oxide intermediate, and it's after this that we see the loss of the leaving group as we reform the pi bond and kick out the chloride. Now the net result of this carbon nucleophile reacting with the acid chloride is the formation of a ketone. And in the presence of excess Grignard reagent, we'll see the ketone further react with that carbon nucleophile to give us yet a second oxide. But now we have a proton transfer step that's required. So either water or dilute acid can be used to protonate this oxide to give us our final alcohol. Now, like we saw for hydrogen nucleophiles, if we want to stop at that intermediate stage, and for this scenario, we'd want to stop at the ketone stage, we need to use a more selective carbon nucleophile than an organolithium or a Grignard reagent. And again, choosing a one equivalent situation isn't going to necessarily give you a major product as the ketone. You'll end up with a mixture of the alcohol and the ketone in those particular scenarios. So we need to use a more selective reagent, and that for this purpose is the Gilman reagent. And the Gilman reagent is shown. This is a lithium dialkyl cuprate. And the idea here is that we're generating our carbanion from this particular species. And so we'll use different dialkyl cuprates depending on what alkyl group we want to incorporate into our final ketone. The mechanism is exactly the same, nucleophilic acyl substitution, where now we have, it's really a transfer of a carbanion from the Gilman reagent. Now this slide nicely summarizes the reactions of acid chlorides. As we saw in this section, the best way to prepare an acid chloride is from the corresponding carboxylic acid using the reagent thionyl chloride. Now once we have the acid chloride, we can pretty much form any other carbonyl containing compound using a variety of reagents. So we saw that if we started with the acid chloride and carried out a hydrolysis reaction, we would end up with the carboxylic acid. In addition, if we carried out that similar reaction, but now in the presence of an alcohol, we would convert the acid chloride to the ester. And in both cases, we use pyridine as a way to neutralize the acidic protons that are produced during this process. We also saw that we could convert acid chlorides to amides, and depending on whether or not we used excess ammonia or excess primary or secondary amine, we could prepare amides or amides with substitution at the nitrogen. We also saw that we could reduce acid chlorides to the corresponding primary alcohol with the use of lithium aluminum hydride followed by a water quench. We introduced two new reagents, one of which was this lithium tri-T-butoxy aluminum hydride, which is a more selective hydride delivery agent in that it will take the acid chloride to the corresponding aldehyde, but not reduce the aldehyde to the alcohol. Similarly, we saw for carbon nucleophiles, we can of course use the Grignard and the organolithium to produce the tertiary alcohol as we've seen previously, but we also introduced a new carbon nucleophile in that of the Gilman reagent. And like the hydride reagent we just mentioned, the Gilman reagent is more selective in that it will react to the ketone, but the Gilman is unreactive towards that same ketone produced. So again, we have a lot of versatility with the acid chloride. We can make any carbonyl containing compound from it, and we can also produce alcohols. So if you have any questions about the reactions of acid chlorides, or if you'd like to review the nucleophilic acyl substitution mechanism, by all means, send me an email. Thank you.